In this video, we're going to talk about the standard deviation. But before we get to the standard deviation, we need to talk about what the standard deviation measures, and that is variability. A large part of science is describing the characteristics of data. Two very important characteristics of data are central tendency and variability. Now, we've already talked about central tendency in a previous video. You know that you have the mean, the median, and the mode, and the type of data you have determines whether you should use the mean, the median, or the mode to describe that given set of data's central tendency. What is the middle? Well, another characteristic of data is variability. And whenever you use the mean as the measure of central tendency, you're going to use the standard deviation as the measure of variability. Now, here's an example of why variability is an important characteristic. Here I have two data sets. The first data set right here has no variability. Its mean is equal to 21. And the second data set has quite a bit more variability. Its mean is also equal to 21. So if we only used the mean, if we only used a measure of central tendency, we wouldn't be able to differentiate between these two sets of numbers, other than listing them, which obviously if it was a very long list, it would be very hard to do that. So what would be nice to have is a measure that reflects how different the scores are from each other. So the most simple measure of variability is the range. And the range, as it says, is not a very precise measurement of variability. Here I have two data sets again, the same different data sets than before, but similar. This first data set right here has a range of 10 because you find the difference between the lowest score and the highest score. 19 is the lowest, 29 is the highest, and the difference is 10. So that data set has a range of 10. The second data set, low score and high score, are the same. So it also has a range of 10. However, obviously all these scores in the middle are different than all of these scores in the previous data set. So the range is what we call insensitive because all of these scores in the middle can be the same or different, and it won't impact the range's value. So it would be nice to have a more precise measurement so that we could differentiate these two different data sets in terms of their variability. And so now we're going to talk about what we're going to be learning for the rest of the video is the standard deviation. The standard deviation is better than the range because it is a more precise measure. It uses every single score in order to compute a measure of variability. So again, I have two data sets. The first data set right here, if I compute its standard deviation, it is 3.52. I'm going to compare that to the second data set. Look at the two data sets. Which one is more variable, do you think? Well, there's more variability in the numbers in the bottom data set, right? They vary more relative to each other. So we would expect, if we have a good measurement of variability, that we would have a higher number, a higher standard deviation. And that is what we get when we compute the standard deviation of the second set of numbers. It is slightly higher because there is more variability in the second data set than the first. Now, I'm going to show you how we actually compute the standard deviation, and we'll talk a little bit more about what it means from here on out. Okay, now there are two ways to compute the standard deviation. There's the definitional method and the computational method. They will always give you the same answer if you do it right. But in order to understand the difference, it's probably a good idea for me to define the standard deviation for you right now. So I will do that. One way of thinking about the standard deviation is the typical deviation of scores from the mean. Now, I'm going to describe what that means for you in a second, but the definitional formula is going to help explain what that definition means. After working through the definitional formula, this verbal description will probably make more sense to you. However, the computational formula won't really help you understand these words. It will, however, be easier for you to actually compute the standard deviation. So there's two purposes. One helps you understand, and the other helps you find the actual value. All right, let's see if that's true. Let's work on computing the standard deviation using the definitional formula. And we're going to pretend like the data that I'm going to give you comes from a population. And what we're going to do is we're going to, X represents the different scores. X minus the mean is the deviation score. We learned about those from in a previous video. And then we have this deviation scores squared. So here is the list of scores I'm going to work with. The first thing I have to do is compute the mean of those scores. So if we add these up, we're going to get 25, and there's 5 scores, so the mean is 5. Now the next thing I have to do is I have to find how far each score is from the mean. So again, all of these are our scores, and we need to find out how far each is from the mean. So 1 minus 5 is -4 away from the mean. 3 minus 5 is -2 away from the mean. 5 minus 5 tells us that there is no distance between those two numbers. And 6 minus 5 is 1. And 10 minus 5 is 5. The next thing we want to do is we want to square each of those deviation scores. And that's what I'm doing here. We have 16, 4, 0, 1, and 25. Now let's just briefly review what we did. We have our raw scores over here. We found their mean. We found each score's distance from the mean, deviation scores right here. And then we squared each of those deviation scores. Okay. The next thing we want to do is compute something known as the sum of squares. And that is the sum of the squared deviation scores. That's basically adding up this column right here. That'll give us 46. Now, why is it called the sum of the squared deviation scores? Because that's exactly what it is. It's the sum of the squared deviation scores. Now, that is often referred to as the sum of squares, or the SS. So whenever you see this set of symbols, we're really talking about the sum of squares, the SS. Well, the SS is a critical step to computing the standard deviation. So we'll do that next. The standard deviation for a population is equal to the sum of squares divided by n, and then you have to take the square root of that whole thing. So in this case, that's going to be 46 divided by 5, and then the square root of that. And that's going to give us 3.033. Now let's think about what this means. I said that the definitional formula is going to help you understand why the standard deviation is thought of as the typical deviation of scores from the mean. We have a standard deviation of 3.03. Now, if you go back and you look at the actual deviation scores, we have some deviations that are more than that. -4 is further away from the mean than the standard deviation. And 5, again, 5 is the deviation score of 10. 10 is 5 away from 5. -4 is the deviation score of 1. It's -4 away from the mean of 5. Those two scores are greater than the standard deviation. Well, we have these other scores here that are less than that. That's always going to be the case. You're going to have some deviation scores that are going to be greater than the standard deviation and some deviation scores that are less than the deviation than the standard deviation. And that's what the standard deviation is trying to show you. It's the typical, or you might even think of it as the average deviation of scores from the mean. So hopefully this definitional formula helps you see what the standard deviation is actually measuring. Again, how far typically, or how far do scores tend to be? Some are going to be more than that, some are going to be less than that, but you can think of it as a kind of average deviation from the mean. Okay, now let's do a computational example. We're going to find the same standard deviation, but we're going to use a different method, the computational method. So here are the same set of numbers. And now what we're going to do is we're going to use this equation. The sum of squares, SS, that's the same SS that we did before, is equal to this equation. So all we need in order to do this is we need the sum of the x's. We need n, which is the number of scores, which is going to be 5. And we need the sum of x squared. So let's get those three things. First, we have to sum up the x's, and if we do that, we get 25. Next, what we have to do, now here's a mistake that people commonly make. They think now, in order to get the sum of x squared, they want to square this 25. Don't do that. That is a common error. Don't do it. First, what you have to do is you have to square each of the x's first. So 1 squared is 1, 3 is 9, 5 is 25, 6 is 36, 10 is 10. You have to do that first. Now, if we add those up, we'll get the sum of x squared. If we do that, we will get 171 for the sum of x squared. Now it's simply a case of taking these numbers and substituting them into that equation. So the sum of x squared is 171 minus the sum of x parentheses squared divided by n, which is 5. If we do that math, it's going to be 171 minus 125 and then subtract that out, we get 46, which of course is the same thing that we got in the previous example. And now we're computing the standard deviation again, which is the sum of squares, which is 46, divided by 5, and then take the square root of all that. Okay. And of course, we're going to get the same answer we got before, 3.033. Now, this is the computation method. This may look complicated to you, but in most situations, this is going to be easier to do than the definitional method. And also, it's really hard to see what this 3.033 means in this formula. It's just an answer you get at the end. In the previous one, we could go back, we could look at the deviation scores, we could say, oh yeah, that kind of makes sense. Here, it's just an answer at the end. So again, different purposes. The definitional formula will help you understand what's going on and what the standard deviation means. The computational formula, it's just easier to get the answer. All right. Now, why do we need these two methods? Well, that's a good question. Each method is better in some situations than others. Now, students tend to really like the definitional formula because, again, it makes sense. It's understanding. And they don't like the particular order of operations that are needed in order to do the computational formula correctly. But in a large majority of the situations, using the definitional formula is going to be problematic. It's going to be it's going to lead to a lot of rounding error. It's going to not be as easy as the other method. Well, let's see if I can prove it to you. So here is a new set of numbers. We have, I've just added some decimal points here. When you have data points that have decimals in them, which happens quite a bit, this definitional formula is going to be harder to use. Well, the first thing we have to do is find the mean. So now I find the mean. There it is. Are you starting to see the problem? The next step, we have to take x minus the mean for every x. So try and do 1 minus 1.3 minus 5.54 in your head. Most of us can't do that. And we're going to have to use a calculator. And the more numbers we have to punch into a calculator, the more likely we are to just make one small button error, and that's going to make our whole answer wrong. So here I did it for us. I took each x minus the mean and found the deviation scores right here. Okay. Now the next thing I have to do is square those. And I did that here. Again, most of us can't do that in our heads. And notice how many decimal places I went out to. If you go out this far, you're going to get an accurate answer, but most people don't. Minimally, you should go out to at least 3 places past the decimal, and then at the very end, round down to 2. But people don't often do that. They stop earlier. They only go to 1 place past the decimal maybe, and then that's going to lead to some rounding error. So the next thing we're going to do is we have to find the sum of squares again. Remember that this thing is equal to the sum of squares. So we have the sum of squares of 46.672. And now we have to take that and plug it into our standard deviation equation. And I've done that here. And notice that we get an answer of 3.0552. That is our standard deviation using the computational method. You can see that this is quite a bit more complicated when our raw scores are not whole numbers and when our mean is not a whole number. Now let's see what that would be like doing this with the computational method. Here are the same sets of numbers. And the first thing I have to do is find the sum of x. The second thing I have to do is find the sum of x squared. Okay, and I've done that. And then I need to substitute those things into the equation. So, again, the sum of x squared gets substituted into the equation. The sum of x gets substituted into the equation. And then 5 is the number of scores. All right, and if we plug through those numbers, notice we're getting the exact same answer that we got before. Oops. Now you can see we get the exact same SS and we get the exact same standard deviation. Now, again, I suppose neither method may be easy, but this one is going to cause you to have to use your calculator a little less, and so it's going to give you a little less chance of making just a button error. And this method, the computational method, has more of an advantage over the definitional method when you have a larger set of numbers. Okay. Now, all of the examples I've been giving you so far have been computing a standard deviation for a set of numbers that I've been calling a population. And so we've been using this equation. Well, most of the time, actually, we'll be working with numbers that are samples rather than numbers that come from a sample rather than numbers that come from a population. But luckily, there's not much difference here. We simply use this equation. We compute the sum of squares the exact same way in both methods, or in both for a population and a sample. The only difference is that you divide the sum of squares by n minus 1 rather than n when you're working with a sample. Another important thing, of course, is to remember is that the symbol for a sample standard deviation is SD, and the symbol for a population standard deviation is this symbol. So hopefully you're more comfortable with calculating the standard deviation, and you have some idea of what the standard deviation means. Throughout this course, you're going to want to be able to compute the sum of squares using both the definitional formula and the computational formula. Knowing both methods will save you time in the long run.